Recording this last lecture here on rotations. I am going to split this up into an A and B lecture because I want to do a chapter 8 wrapper. So this has been a pretty big chapter. So this will be 14A, so I'll have a 14B lecture that just kind of summarizes this whole chapter. Okay. So what we're going to do now, so let's look at the learning goals right here, okay? So we're getting into these last few learning goals. And so today we're going to talk about this space quantization and the vector model. So we're going to discuss that. And assuming I've left myself enough time, we're also going to talk about electron spin. Because as it turns out, of course, electrons spin, and so we can use the same considerations we've been working with in these rotation lectures to describe electron spin. Okay, so great. So let's put this away. And so we're going to get into this vector model. And so just to kind of remind you, we've already talked about the right-hand rule for angular momentum. But I also want to remind you, if let's suppose I have some vector, okay, so I'll draw like a XYZ coordinate system. Okay. Perhaps this is X, Y, and Z points up. All right. So if I draw some vector, so I'm going to draw some vector in the going into the ZY plane, right? So, and I don't know why I chose to draw this so small, but we're going to go with it. So that vector, I'll remind you, has components in the z, x, and y dimension, depending on how we've drawn it. Of course, this one I've only drawn in the z, y plane, which means now if I'm going to change my color here. So that means this vector would have projected magnitude on the z-axis, or really I should say projected length on the z-axis. It would have also projected length on the y-axis, right? And if I add those two projected lengths up, then I get the total magnitude of the vector, okay? So let's label those. Let's say total magnitude. And of course, that total magnitude is going to give me the length of that vector. And I'm going to call these, the blue areas, the projected lengths. Okay. And of course, with this vector, the way I've drawn it, we'd have projective lengths on the z and the y. But what if I gave my vector some pitch, right, out into that x dimension? So then, of course, we would have projected lengths on the x, y, and z, and we would have to use this full three-dimensional cross product to describe that vector. And more importantly, what we're really interested in, right, is describing this vector as angular momentum, right? So if you look at my picture here, and I just noticed I got this picture from Atkins, and it's drawn wrong. They violated the right-hand rule. So right, if that vector is pointing up this way, it should be rotating the opposite way. In any event, right, when we see pictures like this, we want to represent this angular momentum as this three-dimensional vector representation, okay? So here's how we do it. We use the determinant, okay, R cross P. And so you might have just talked about this very, very briefly in some of your math classes, but I'm going to go through this to remind you, okay? So L hat. So now when I go through this, okay, I'm going to start with, vector I, right? So each of these vectors, I, J, K, give us the, the projected X, Y, and Z vectors, right? That's what the I, J, K stand for. And so the way that I do this, okay, so if I start with I, then I go down the diagonal, right? and that's going to be y times pz minus z times py. Okay, so I'm going to put that in red so that we can see what's going on. So I'll say dot, 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 dot. We start at I, and we go to y. Okay, and so then we say y times pz minus z times py. All right, so that's going to look like this. Let's see here. Y hat pz hat minus z hat py hat, parenthesis, and that's all times vector I. Okay, and so now we've got to keep going with the other dimensions. And so I didn't leave myself enough room, so I'm going to, on this next line down here, I'm going to say minus. So right, we keep summing up all of these projected lengths. And so now when I go to j, all right, let's get a different color for j. So when I go to j here, I'm going to now go over, I'll draw a dot to the x, okay? And now I do this diagonal, okay? So where I'm going to go now x pz and z px, okay? So that gives me like so and like so, okay? So let's see here. So now I've got that as x, yep, x pz minus z px, okay? For some reason, I just doubted myself for like half a second, so I'm just going to verify that I did that correctly. Yes, x pz minus z px, okay. Beautiful. So there's the z, and then now that's times vector component j. And then now finally when I do my k, that's an addition. Okay, so this is just standard matrix manipulations. And I'm going to go with a slightly different color. So now if I start with k here, k, I'm going to go down to y. Okay, and then oops, wait a second. Nope. I was about to do it wrong. Let's say undo, 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 undo. Okay, so now I'm going to go k all the way out to the x. Okay, and now I go x py y px. Okay, great. Okay, so now that's going to be x py minus y px times vector length k. All right? And so now what does all of this stuff get at? Well, what we have now is a total orbital angular momentum operator. And what becomes useful is now for us to think of each one of these as the two-dimensional representation that we talked about earlier. So let's go all the way back to, yes, to right here, okay, when we were doing this two-dimensional. So now you can see this is where these two-dimensional results come from, okay? And you also, hopefully you recall that the eigenvalue for each one of those was MLH bar. So what we can do with this now, let's see here. So I'm going to call this I component, so this y pz minus z py, I'm going to call that Lx operator, okay, times the I vector, right? Minus, and then xpz minus z py is going to be Ly operator times the j vector, okay? And then now we go plus for the k dimension, which is z, and xpy minus ypx is going to be Lz times the k vector. And so now if I had a picture that looks like this, right, where you can see I have this particle that not only has projected magnitude in the ZY plane. It also has projected magnitude in the ZX plane, and it also has projected magnitude in the XY plane. Okay, so this would be my total operator that I want to use. But something interesting is going to happen. Okay. Oh my gosh, look at that. I left myself a whole blank space. So what's going to happen now is, so recall that position and momentum are suspect to Heisenberg uncertainty, right? So each one of these terms, YPZ for example, that's going to have a Heisenberg uncertainty. ZPY, that's also going to have a Heisenberg uncertainty, right? Any of these terms in our orbital angular momentum operator are going to be suspect to Heisenberg. So what happens if we look at the commutator between those individual operators? So for example, if I look at the commutator between the y dimension and the x dimension, okay? And so recall this commutator, right? We go Lx, Ly operate on psi, minus Ly, Lx operate on psi. And if these are equal to 0, there's no uncertainty. But if they're equal to non-zero, there is an uncertainty. And as it turns out, the commutator between Lx and Ly is given by I h bar Lz, which is kind of cool actually, because I'll remind you, so recall in just our two-dimensional standard translational Heisenberg uncertainty model, right, where we just looked at position and linear momentum. So recall the commutator between those two was IH bar, right? So it's kind of cool that this works out to be IH bar LZ. And so what this means is if I try to specify with arbitrary precision the angular momentum projected length in the x and y dimensions, I will have uncertainty in the z dimension. Well, what do you want to bet is going to happen if I switch those dimensions? So if I look at now the commutator between Ly and Lz, if you're saying IH bar Lx, then you're getting it. So IH bar Lx. So now, if I try to specify with great precision the projected length of orbital angular momentum in the y or z dimension, I have uncertainty in the x dimension. And of course, finally, if I do this for the last pair, which would be Lz and Lx, of course, I'm now going to have uncertainty in the y dimension. Okay? So how the hell are we going to do this, right? How are we going to specify this particle's total orbital angular momentum if by trying to specify any two dimensions, I then get uncertainty in the third dimension? Okay. Well, the answer is that if we specify one specific dimension, which we're going to give special treatment to the z dimension, and that's just arbitrary. We could have picked x, we could have picked y. But as it turns out, as we keep going down the rabbit hole in this class, we're going to give special treatment to the z dimension. And that's just based on this right-hand rule, okay? That if I'm rotating in the xy plane, I have angular momentum in the z dimension. But if I pitch this thing, right? So if I go back and draw my coordinate system, y and x and z, well, if I allow this to pitch, okay, look, this vector is still going to give me some projected length on the z dimension, okay? Of course, there's going to be projected length on the other two dimensions. So we're going to give special treatment to the z for one, but also what if we give special treatment to just this total magnitude? So remember, if I go back to our vector review, remember the one that's going out in that angle theta phi, that's going to give us our total magnitude of those two projected lengths. So what if we try to specify with great precision the magnitude? Okay, well, that becomes pretty cool. And so what we get, so to do that, right, so first of all, to get the total magnitude, I think this is why I have so much extra space, all right? So we recognized that when I look at the angular momentum here, it was Lx, okay? And I'm gonna drop the vector ijk because we recognize that that is just meant to signify that it's a vector in those specific dimensions. So if I want to know the total magnitude of this vector, then in vector math, what I do is square this operator, okay? So total magnitude is given by the following: L squared, which is going to be Lx squared plus Ly squared plus Lz squared, and this is going to create a Pythagoras triangle, which is very cool, and we're going to see that coming up. And also, I'll just kind of supply for you this value here. When we go through all of this, it's a pretty cumbersome result. It equals h bar squared over, or h bar squared times the Legendran squared. And recall that Legendran squared, right, is that big nasty 1 over sine squared theta, et cetera, et cetera, et cetera. Okay. Well, as it turns out, so here I've got that all summarized right here. If we now look at the commutator between the magnitude and any one dimension, x, y, or z, then we have no uncertainty, okay? Which is awesome. So therefore, and right, we have no uncertainty because that equals 0, okay? So therefore, although we may specify the magnitude of angular momentum and any of its components, if, and here, this is where we're giving special treatment to LZ. So we noted here that this could be X, Y, or Z, but we're going to choose Z for arbitrary reasons. So if LZ is known, then it is impossible to ascribe values to the other two components. So that's kind of saying what we discovered here, all right? And I probably should have put another line here. But now, if LZ is known, and we know the total magnitude, then we no longer have a Heisenberg uncertainty principle situation at hand, okay? So how does this play out, all right? Well, let's review some of the things that we've already come up with, and we're gonna see how this manifests on this vector model, okay? So recall, the particle on a ring. Energy solutions were Jz squared over 2i, which is also equal to ml squared h bar squared over 2i, and thus my quantized angular momentum is ml h bar. And specifically, I know it's a J sometimes and an L sometimes, but capital JZ is specific to the angular momentum on this Z dimension for a particle rotating on a ring, okay? We get ml h bar values. So when we did particle on a sphere, all right, we got that the energy solution is L times L plus 1 times h bar squared over 2 times I, all right? And so what we are seeing here, what's pretty cool, is now we have ways of connecting the projected Z length and the total magnitude, okay? So if you look at how these two equations connect now, what we can now say is our total magnitude, which is going to be this LZ squared, all right, is going to be equal to our JZ squared result, which is L times L plus 1. What did I do here? I'm going to erase all of this. I'm going to start over. So basically what ends up happening, right, is that we get Jz here equals mlh bar for this particle on a ring for the two-dimensional model. And expanding that out into 3 dimensions, the total magnitude becomes L times L plus 1 square root h bar. Okay? So that comes from substituting the fact that we've got this mlh bar, ml squared h bar squared, and L times L plus 1 h bar squared. Okay? So here we're going to see this mlh bar is our projected z length, and this L times L plus 1 h bar is our total magnitude. Okay? So I'll remind you also that angular quantum number L takes on values 0, 1, 2, etc. Our magnetic quantum number takes on L dependencies, so ml equals L, L minus 1, etc. Okay? And then from this ml, we get this 2L plus 1 values of ml. So how do I get 2L plus 1? So let's go through this. So if L is equal to 0, ml has to be equal to 0, meaning Jz has to be equal to 0. And if L is equal to 0, 2 times 0 plus 1 is just 1. So there's only one degenerate state for ml equals 0. So that's what this Jz2L plus 1 degeneracy is. What if L is equal to 1? Well, then we know ml is -1, 0, +1. And so that means Jz can take on values of 0 or plus or minus h bar. Okay? And so the number of degenerate Jz states is 3. And we get 3 because if L is 1, 2 times 1 plus 1 is 3. Okay? And then so on. If we have L is equal to 2, then ml can be -2, -1, 0, +1, -1, -2. We can see the values, the permitted values of Jz, and then of course the number of degenerate states. Okay? If you're seeing connections to the periodic table here, then you've got a really good eye, because that's what's coming. Okay, so now, how do we connect these two things? I'm going to draw an arrow and a question mark. How are these two ideas connected? All right, so I think this is where this gets really cool. Okay, so if, and I wrote here Jz squared, but really that's Lz operator squared, because it's the total magnitude. All right. So if the z component, the projected z length, is mlh bar, and here let's make a coordinate system. Okay. So I'm going to draw that right here with my origin starting at this triangle, where now this is, let's call it x, y, and z. Okay. So now we can see my z component of the vector is given by mlh bar. And what's important to note is I know this value. We know this. So because if we know the quantum number ml, then we know what the projected length is, right? If ml equals 1, then we know that this length, the length of this vector, is h bar. If ml is equal to 2, then we know that this is 2h bar. Okay? So then what about this? Well, my projected magnitude is given by root L times L plus 1 h bar. Okay? And I can turn that magnitude into projected length by taking the square root. And so now I get that the length of this vector becomes root L times L plus 1 h bar, and this makes a 90-degree triangle. And the reason why it makes a 90-degree triangle is because we know this length and we know this length. And remember that my particle is going all the way around full circle. Okay? So that means this length has to be fixed and given by the angle theta. How do we get that angle theta? Well, SOHCAHTOA, right? Remember, cosine is the adjacent over the hypotenuse. And based on the way that I've drawn this picture, we can see the cosine of theta is then going to be the adjacent, which is ml h bar, or just ml at this case, over the hypotenuse. So what this means now, all right, we can specify the projected length. We can specify the z component of the vector, that with no uncertainty situation whatsoever. And now what we get out of this theta is we learn what that angle is. So in other words, back to my same z, y, x coordinate scheme, I'm going to use a different color. What that means now is the way my particle is rotating, right? In the two-dimensional model, it was just going straight up. But you can see, right, this is given by my projected length. So this is accurate by calling this jz, my projected length here. Okay? So that means this particle has to be pitched out by angle theta, which it means it's going to be rotating around like this. Okay? Very cool. And so now what we see is by having different values of ml, we have different z lengths. And if the jz value is fixed because they're all degenerate for a given value of L, that then predicts as the ml value is changed, we get different angles of rotation. Okay, so I should say different angles of our orbit. So here's what that looks like. So suppose L is equal to 2. So then we know that we can have ml equal to +2, +1, 0, -2, and -1. Are all of those states degenerate? Well, let's think about it. So if L is equal to 2, right, then we know that projected, then we know that, the angular momentum is given by the square root of 2 times 2 plus 1 times h bar. 2 plus 1 is 3 times 2 is 6. So in other words, all of these jz lengths will be root 6 h bar. Okay, so let's look at this picture right here. ml plus 2, the length of this arrow is root 6 h bar. ml equals 1, the length of this arrow is still root 6 h bar, and etc. So I'll keep writing those in. They're all length root 6 h bar based on my, I don't know why I wrote root 6. So root 6 h bar. Okay, so that makes them all degenerate because they all have the same angular momentum. So in other words, because they all have the same angular momentum, that means they have the same frequency of rotation, right? They're all rotating the same. And so the only thing that changes now is as ml changes, it's just changing the way that this pitches out in that other dimension. So for example, when ml is plus 2, we know now that this length is 2 h bar, okay? When ml, and so I'll draw that right here. When ml equals 1, we know that this length is just h bar, and because that adjacent length has shrunk, that means my angle theta has to increase by SOHCAHTOA, right? And so that's describing that extra pitch from the ml plus 2 state to the ml plus 1 state. Very cool. And so what you can also see, ml equals 0, there's no angle whatsoever because ml equals 0, there's 0 z component. So this describes a particle that's rotating perfectly in the z plane. We're going to see that this ml equals 0 is a special case as we start building up our description of the atomic orbitals. And we'll see that ML equals 0 is specific to the z-axis. I know that we don't have angular momentum in the z-axis, right? Our angular momentum is pointing out that way, but our rotation is occurring in the z-axis, okay? So now I just drew the ML equals 0 state again, just so now we can compare that to the ML minus 1 state, right? So now this length is minus h bar, so it's still h bar, but it's just now in the other direction. And of course, now this length is minus 2 h bar. And so now I'll also remind you, our particle is spinning round and round, right? And if you recall, when we did our square modulus of psi ml, that result was 1 over root 2 pi. So that means no phi dependence. Okay, so when we look at this picture over here, so remember, out this way is theta, and this way is phi. So the fact that our wave function has no phi dependence means it's spread out over all angles of phi. So what we get from this space quantization are these projected cones, okay? So these projected cones represent our angular momentum, right? So you can see here is that +2 state, okay? And we can see the particle is spinning round and round and round, but because we know that there's no phi dependence, then that, right, that root 6 h bar at angle theta, okay, it smears around all phi angles, okay? So this is what we call, this is the space quantization model, all right? So it's important to note that this is not psi squared. This is not where like we expect the particle to be. It really just kind of represents the fact that we still do have a Heisenberg uncertainty situation going on, okay? And that Heisenberg uncertainty situation is Jz and phi, right? So we can specify this length here, but because we don't know where the particle is on this angle phi, that's what predicts this spreading all the way around. So we still have uncertainty in our angular momentum, but we've narrowed it down to these conical areas. Okay, continuing along. As it turns out, electrons can spin too. So I'm kind of shifting gears here, okay? And so, you know, we've described this picture of like some center of mass and some electron spinning around that center of mass, okay? But also this electron itself can rotate about its own center of mass. So this is much like our solar system picture, right? Where we've got, you know, here's Earth spinning around 24 hours in a day, but then also 365 days to make it all the way around. So what that means is there's actually two contributions of angular momentum as a result. There's the orbital angular momentum, right? But then there's the electron spin angular momentum, okay? This is going to become really important in spectroscopy. And a result, what's really cool about this, if you look at the hydrogen atomic emission spectrum, you have to have a very, very precise spectrometer to do this. But if you were to zoom way into the red line at 656.3 nanometers, you would actually see that it's a doublet. And the reason why that's a doublet is because, recall, in hydrogen, it's got one unpaired electron, okay? So if its spins are correlated, so in other words, if the picture looks like this, that's going to be a system, or excuse me, there's going to be a specific energy associated with this system. But if it's spinning the other way, I'll draw that picture down here. So let's say it's still orbiting around in this dimension, or in that orientation, to give you orbital angular momentum that points in that direction. But let's say it's a downward pointing electron, right? So it's pointing, so it's spinning the opposite direction and pointing down. The way that those two angular momentums couple create different energy transitions. And as a result, with this unpaired electron system, you see a doublet due to the electron orbit spin coupling, is what we call that. And we're going to come back to this in more detail in spectroscopy, okay? So the way that this was first discovered was in the very famous Stern-Gerlach experiment, where they took silver atoms, okay, and they, did they ionize these silvers? I want to say that they had to ionize them to get them to do this thing here. Let's see. Well, in any event, we looked at silver atoms because, as it turns out, silver has one unpaired electron. I'm looking for my periodic table right now. Let's see here. Yes, it had to be silver atoms because if you look at silver plus, right, the 4s or 5s2 fills over and fills the shell. So we know that then that's really, right, 5s1, 3d, sorry, 5s2, 3d9, okay? So if electrons weren't spinning, okay, so what they did in the Stern-Gerlach is they had this big magnet north-south pole, okay? And if electrons weren't spinning, then what you would expect is as these atoms expanded into this evacuated region, so this side was vacuum, which is going to give you that throttling expansion, okay? Then what they would have expected is, a silver atoms like would be all over the place. Like they're, you would see like a spread of them hitting that phosphorus screen. But that is not what happened. When they separated those atoms in a magnetic field, they got atoms that would either hit the screen right there or atoms that would hit the screen right there. And those results are what led them to conclude that electrons themselves must also be spinning. And so there's loads of examples that we'll see in spectroscopy that gives evidence of these kinds of things, these doublets, right, that show us that electrons spin. And that their spin, angular momentum, couples with their orbital angular momentum, which is very cool, all right? So, and of course, we can come up with the same situation in this vector model. So as it turns out, so the spin magnetic quantum number, ms, is given by s minus 1, all the way down to negative s. As it turns out, there's only one quantum number for electrons, and that's s equals 1/2. We can come up with spin quantum numbers for other particles as well, like photons or neutrons or protons, and they have different values of s. S equals 1/2 for electrons. And because ms takes on all values s minus 1, negative s, this means for an electron, ms can be plus or minus 1/2, okay? And just like we saw with orbital angular momentum, electrons are also suspect to the same Heisenberg uncertainty principle. The z component of their vector is given by ms h bar. The projected length is given by s times s plus 1 h bar. And we can make the same picture right here that we just did. And they have the same conical representation of their angular momentum. All right? So I've been talking for quite a bit, so I'm going to wrap that up, and I'm going to record one more very quick short lecture after this that's going to be kind of like a wrapper for this whole chapter. Okay?